About 541 million years ago, the prehistoric era began, bringing a world filled with giant reptiles, unusual sea creatures, early mammals, and large forests unlike those found today. But what if that ancient era had never ended? Dinosaurs would still live across many parts of Earth, large flying reptiles would still exist, giant insects would live in warm forests, and early human ancestors would have shared the planet with these animals. Everyday life would be shaped by the need to live among powerful, prehistoric creatures. Plants, animals, climate, and the growth of human societies would all develop in different ways. Millions of years ago, the Earth was home to giant reptiles, ancient forests, strange sea animals, and flying creatures that ruled the skies. During the prehistoric era, life developed in many different forms over a very long period of time. Dinosaurs walked across huge plains, thick forests covered large areas of land, and warm oceans were filled with reptiles, fish, and many kinds of sea life. Small mammals lived quietly among these larger animals, while early birds began to spread through the skies. This long period of Earth's history eventually came to an end, after a series of natural events changed the planet forever. Many of the largest animals disappeared, and new forms of life slowly became dominant. Humans appeared much later and eventually built towns, cities, farms, and modern civilizations. Now imagine that this great change never happened. Imagine that the prehistoric era continued without interruption, and that the giant reptiles, ancient plants, and other prehistoric life remained the dominant forms of life across the planet. Earth would be a very different place. Every continent would still be filled with animals that had ruled for millions of years. Many species that disappeared in real history would still be alive, while many modern animals might never have appeared at all. The land would be covered with enormous forests stretching across valleys, mountains, and wide plains. Many of these forests would be made up of ancient trees such as conifers, cycads, tree ferns, and ginkgo trees. Flowering plants might still exist in some places if they had continued to evolve, but many regions would remain dominated by older kinds of plants that had already become successful long before modern forests appeared. Thick layers of ferns would cover the ground beneath the taller trees, creating cool and damp habitats for countless small animals. The climate in many parts of the world would remain warmer than it is today. Large areas near the poles might never develop permanent ice sheets. Instead, forests could grow much farther north and south than they do today. Seasonal changes would still happen, but the difference between summer and winter in many regions would be smaller. Warm temperatures would allow reptiles to remain active across much larger parts of the planet. Dinosaurs would continue to fill almost every land environment. Small dinosaurs would search for insects among the plants. Medium-sized plant eaters would move through forests in groups, feeding on leaves, shoots, seeds, and other plant material. Giant long-necked dinosaurs would slowly travel across open land, reaching leaves high above the ground. Their enormous bodies would require huge amounts of food every day, forcing them to keep moving from one feeding area to another. Large meat-eating dinosaurs would remain the highest predators on land. Different species would occupy different regions, each adapted to local environments. Some would hunt in forests where thick vegetation provided cover. Others would live on open plains where they could spot prey from long distances. Coastal predators would hunt near rivers and lakes where many animals gathered to drink water. Their survival would depend upon strong senses, powerful muscles, and successful hunting strategies passed from one generation to the next. Smaller predators would also play important roles in prehistoric ecosystems. Fast-running dinosaurs would chase small animals through dense vegetation. Feathered hunting dinosaurs would use sharp claws to catch prey. Some might hunt alone, while others could live and hunt in groups, depending on their species. These smaller hunters would help control the populations of insects, reptiles, mammals, and young dinosaurs. The skies would remain crowded with flying reptiles known as pterosaurs. Some would have wings wider than many modern aircraft. Others would be much smaller and spend their time searching for insects, fish, or small animals. Coastal cliffs would provide nesting places where thousands of flying reptiles could gather during breeding seasons. Inland lakes would also attract large numbers of these flying animals because of the steady supply of fish and fresh water. Birds would continue evolving alongside pterosaurs. Some bird species might remain small forest animals, while others would grow much larger over time. Since pterosaurs would still dominate many parts of the sky, birds might develop different feeding habits or occupy habitats where competition was lower. Some could become expert swimmers, while others might specialize in forest life or mountain regions. The oceans would remain filled with giant marine reptiles. Long-necked plesiosaurs would swim through coastal waters searching for fish and squid. Fast-moving ichthyosaurs would chase schools of fish across open seas. Huge mosasaurs would patrol warm oceans as top marine predators. Coral reefs would support countless smaller creatures, including shellfish, sea stars, sea urchins, and many kinds of fish that had evolved over millions of years. Ancient sharks would continue evolving as well. Some species would grow into powerful ocean hunters capable of attacking large prey. Others would remain small bottom feeders that searched the sea floor for food. Rays, primitive fish, and many other marine animals would form complex food webs that supported the rich life of prehistoric oceans. Rivers would flow through dense forests filled with ancient reptiles. Crocodile relatives would bask along muddy riverbanks, waiting for animals to approach the water. Giant turtles would swim slowly through lakes and wetlands. Amphibians would continue living in moist environments where they laid eggs and hunted insects and other small animals. Insects would remain one of the most successful groups of animals on Earth. Beetles, dragonflies, ants, termites, flies, butterflies, and many other insects would continue evolving beside dinosaurs and prehistoric plants. Some insect groups might grow much larger in warm climates where oxygen levels and environmental conditions allowed them to thrive. Forest floors would constantly move with countless small creatures carrying out important roles such as pollination, decomposition, and soil formation. Small mammals would still exist, but their development could follow a very different path. Instead of becoming the dominant land animals after the disappearance of dinosaurs, they would continue sharing habitats with giant reptiles. Many mammals might remain small enough to hide underground, climb trees, or remain active mainly at night. Their intelligence could continue increasing, but their body size might stay limited because of constant pressure from larger predators. Some mammals would specialize in eating insects, others would feed on seeds, fruits, or small reptiles. A few could become skilled climbers that spent almost their entire lives in the forest canopy. Burrowing mammals would dig complex tunnel systems beneath the ground, providing protection from predators and extreme weather. These underground homes would also serve as places where mothers raised their young in relative safety. If early human ancestors eventually appeared in this world, their lives would be completely different from the history known today. Every journey across open land would involve the danger of meeting large predators. Settlements would need strong walls, watchtowers, and safe shelters built from heavy materials. People would learn to recognize the sounds, tracks, and behavior of many dangerous animals from an early age. Early farming would face many challenges. Large plant-eating dinosaurs could destroy fields within a short time if they entered growing areas. Farmers would need strong fences, deep trenches, and constant guards to protect their crops. Smaller dinosaurs and prehistoric mammals might also feed on fruits, vegetables, and stored grain, forcing people to develop new ways of protecting food supplies. Domestic animals might be very different. Dogs, horses, cattle, sheep, and goats might never become common if their ancestors failed to survive under prehistoric conditions. Humans might instead tame smaller prehistoric reptiles or certain dinosaur species that showed calm behavior and could be trained over many generations. Some could carry loads, help guard settlements, or assist with farming work. Trade between distant communities would become more dangerous because travelers would need to cross forests filled with large predators. Rivers could offer safer travel routes, although giant crocodiles and other aquatic predators would still create serious risks. Boats would become an important method of transportation, allowing people to move goods while avoiding some of the dangers found on land. Cities would likely develop only in carefully chosen locations. Natural cliffs, islands, or areas surrounded by water would provide extra protection. Defensive walls would be much thicker than those built in many ancient civilizations. Large gates would remain closed whenever dangerous animals approached. Watchmen would constantly observe the surrounding landscape for signs of approaching predators or migrating herds. Education would include learning about prehistoric wildlife. Children would study animal tracks, warning calls, seasonal migrations, and safe behavior around dangerous species. Hunters, farmers, builders, and travelers would all need detailed knowledge of local ecosystems to survive. Medical knowledge would also develop differently. Injuries caused by large reptiles, venomous animals, and powerful bites would be common. Doctors would study wounds, infections, broken bones, and poisonous plants that could either heal or harm people. Communities would collect useful herbs growing in prehistoric forests and learn how to prepare medicines from natural sources. People would also study dinosaur behavior carefully. Some species might migrate every year in search of fresh vegetation. Others would remain within fixed territories. Understanding these patterns would allow communities to avoid dangerous encounters and plan farming, hunting, and travel more safely. The sound of this world would be very different. Forests would echo with the calls of dinosaurs, the cries of pterosaurs, the songs of birds, the buzzing of insects, and the sounds of countless animals moving through thick vegetation. During the night, many predators would become active while smaller animals searched quietly for food beneath the cover of darkness. Large volcanic regions would continue shaping parts of the planet, creating new land, changing rivers, and covering forests with fresh layers of volcanic material. Earthquakes would sometimes reshape valleys and coastlines, forcing both animals and people to adapt to changing landscapes. Rivers would change direction over long periods, creating new wetlands while older lakes slowly disappeared. Different continents would support unique groups of prehistoric animals because long periods of isolation would allow species to evolve separately. Dinosaurs living in one part of the world could look very different from those living elsewhere. Forests, deserts, mountains, and wetlands would each support their own distinct communities of plants and animals. Human knowledge of nature would become one of the most valuable skills in society. Survival would depend not only on strength, but also on understanding the habits of the countless prehistoric creatures that continued to rule the earth. In this world, every season would bring changes that people and animals would have to understand. During warmer months, many dinosaurs would lay eggs in carefully chosen nesting grounds. Some species would build large nests from plants, soil, and small branches. Others would dig shallow holes in sandy ground before covering their eggs. Parent dinosaurs might stay nearby to protect their nests from hungry predators, while some species could leave the eggs shortly after laying them. Newly hatched dinosaurs would face many dangers from the moment they emerged. Small meat-eating dinosaurs, large reptiles, birds, and mammals would all search for young animals that were easy to catch. Only a small number would survive long enough to reach adulthood. Large groups of plant-eating dinosaurs would travel together to improve their chances of survival. Living in herds would allow many eyes to watch for danger at the same time. Adults would often remain close to younger members of the group, protecting them from attacks whenever possible. These herds could contain hundreds or even thousands of animals moving across open plains in search of fresh plants. Their movement would create clear paths through forests and grasslands, while their feeding would shape the growth of many plant species. The ground itself would show constant signs of prehistoric life. Huge footprints would press deeply into soft soil near rivers and lakes. Long trails would mark the regular paths used by migrating herds. Broken branches, stripped leaves, and damaged trees would show where giant animals had recently passed. Hunters, travelers, and scientists would learn to read these signs carefully, because they could reveal which animals had been nearby and how recently they had moved through the area. Weather would continue to influence the lives of every living creature. Heavy rains could flood valleys and fill rivers, forcing animals to move toward higher ground. Dry seasons would reduce the amount of fresh water available, causing many species to gather around permanent lakes and rivers. These crowded watering places would become dangerous because predators would know exactly where prey animals were likely to appear. Deserts would also exist in many parts of the world. Even in a prehistoric Earth, not every region would be covered with forests. Dry landscapes would support animals specially adapted to survive with limited water. Certain dinosaurs might travel long distances between water sources, while others could obtain enough moisture from the plants they ate. Reptiles with thick skin would lose less water, allowing them to remain active even during long dry periods. Mountain regions would provide very different environments. Cooler temperatures and steep slopes would create habitats where only certain species could survive. Smaller feathered dinosaurs and early birds might live among rocky cliffs and mountain forests. Mammals adapted for climbing could also find safety in these difficult landscapes where larger predators had trouble following them. Fast rivers flowing down mountain valleys would provide fresh water for both wildlife and human communities. The oceans would remain one of the richest parts of this prehistoric world. Large schools of fish would travel through warm seas, while giant marine reptiles followed them during seasonal migrations. Whales might never evolve into the forms known today if marine reptiles continued to dominate the oceans. Instead, many ancient sea reptiles would keep expanding into new habitats, developing new hunting methods and different body shapes over millions of years. Coral reefs would support thousands of species. Brightly colored fish, shellfish, sea snails, sea cucumbers, and many kinds of small sea animals would live among the coral structures. Larger predators would patrol nearby waters, feeding on the smaller creatures that depended on the reefs. Storms could damage these underwater habitats, but living coral would slowly rebuild them over many years. Freshwater lakes would become centers of life. Fish would attract birds, reptiles, and mammals, while the surrounding plants would provide food for many plant-eating dinosaurs. Wetlands filled with reeds, ferns and other water-loving plants would support frogs, insects, turtles and countless small animals. Thick mud along the shores would preserve footprints left by passing dinosaurs, allowing future scientists to study their movements. If humans developed advanced science in this world, paleontology would be very different. Instead of studying fossils from animals that disappeared long ago, scientists could observe living prehistoric species directly. They could watch dinosaurs raise their young, study how they communicated, record their migration routes, and learn how different species interacted with one another. Fossils would still be important because they would reveal the long history of prehistoric life and show how living species had changed over millions of years. Biologists would spend their lives studying dinosaur behavior. Some species might communicate through deep sounds that carried over long distances. Others could use body movements, colorful feathers, or changes in skin color to send signals. Scientists would carefully record these behaviors, helping people understand how to avoid dangerous situations and how different species live together. Veterinarians would become experts in treating prehistoric animals. Zoos, wildlife parks and research centers might care for injured dinosaurs that could later return to the wild. Caring for a giant dinosaur would require large medical equipment, powerful lifting machines, and teams of trained specialists. Even treating a broken leg or infected wound would be a major task because of the enormous size of many animals. National parks would cover vast areas of untouched wilderness. These protected lands would preserve ancient forests, wetlands, mountains and coastlines where prehistoric animals lived naturally. Rangers would patrol these parks to protect both wildlife and visitors. Observation towers, secure vehicles and protected walking paths would allow people to study nature while reducing the risk of dangerous encounters. Tourism would become one of the largest industries in many countries. Visitors from around the world would travel to see living dinosaurs in their natural habitats. Guided tours would follow strict safety rules. Visitors would remain inside specially designed vehicles while trained guides explained the behavior of nearby animals. Observation stations built high above the ground would allow safe viewing of nesting sites and migration routes. Photography would become an important scientific tool. Powerful cameras with long-distance lenses would capture images of shy or dangerous species without disturbing them. Drones could fly above forests and wetlands to count animal populations and monitor seasonal movements. Satellites orbiting Earth would help scientists track large herds across entire continents. Modern cities would need special designs to protect people from wildlife. Green areas inside cities would be carefully managed so they did not attract dangerous animals. Strong barriers would surround roads, railways and airports to prevent large dinosaurs from entering busy transportation routes. Warning systems using cameras and sensors would alert people whenever dangerous animals approached populated areas. Roads passing through prehistoric habitats would include tunnels, bridges, and wildlife crossings. These structures would allow migrating animals to move safely without blocking transportation. Engineers would study migration patterns before building new highways to reduce conflicts between human activity and wildlife. Railway systems would also require strong protection. A collision between a fast train and a giant dinosaur could cause serious damage. Fences, warning systems, and careful route planning would reduce these risks. In areas where large herds migrated every year, trains might stop temporarily until the animals had safely crossed the tracks. Air travel would face unique challenges because of large flying reptiles. Airports would use advanced radar systems to detect flocks of pterosaurs approaching flight paths. Air traffic controllers would direct aircraft away from areas where flying reptiles gathered in large numbers. Scientists would also study seasonal movements to reduce the chance of dangerous encounters. Agriculture would depend heavily on technology. Farmers would use strong electric fences, observation towers, and automatic warning systems to keep large animals away from valuable crops. Some farms might even employ trained prehistoric animals to help guard fields against wild species. Food production would include many ancient plant species that no longer exist in the real world. Some prehistoric fruits, seeds, and edible ferns could become important sources of nutrition. Scientists would carefully study these plants to determine which were safe to eat and which contained harmful chemicals. Medicine would also benefit from prehistoric biodiversity. Many ancient plants could contain natural substances useful for treating disease. Researchers would search forests and wetlands for new compounds that might become valuable medicines. Venoms produced by prehistoric reptiles and insects could also provide useful materials for developing new medical treatments after careful study. Education would include regular field trips into protected natural areas where students could safely observe prehistoric ecosystems. Children would learn to identify different dinosaur species, understand food chains, recognize animal behavior, and respect the dangers of living alongside large wild creatures. Schools would teach survival skills as part of everyday education. Books, films, and artwork would often focus on prehistoric wildlife, because these animals would be part of everyday life. Artists would paint scenes showing migrating dinosaurs, nesting pterosaurs, and ancient forests. Writers would create stories about explorers, scientists, park rangers, and communities living beside giant animals. Religions and cultural traditions might also develop around prehistoric life. Some societies could view certain dinosaur species as symbols of strength, wisdom, protection, or good fortune. Festivals might celebrate the arrival of migrating herds or the return of nesting seasons. Ancient stories passed through generations would describe important encounters between humans and prehistoric animals, becoming part of each culture's history. Music and language might even contain sounds inspired by the calls of dinosaurs and other prehistoric creatures. Place names could come from famous nesting grounds, ancient forests, or rivers known for large reptiles. Many communities would build their identity around the wildlife living nearby. Scientists would continue discovering new prehistoric species because evolution would never stop. New populations separated by mountains, rivers, or oceans would slowly develop different features over countless generations. Some dinosaurs might become smaller as they adapted to island environments. Others could grow larger in regions with abundant food and few natural threats. Genetics would become an important field of study. Researchers would examine how prehistoric animals inherited traits such as feathers, horns, body armor, strong jaws, or large body size. This knowledge would help conservation programs protect endangered species and maintain healthy populations across the world. Conservation would become one of humanity's greatest responsibilities. Even in a world where prehistoric animals survived, habitat loss, disease, climate changes, and human activity could threaten certain species. Governments and international organizations would work together to protect ancient ecosystems, so future generations could continue living alongside the remarkable creatures that had shared Earth for millions of years. The balance between humans and prehistoric wildlife would require constant attention. Expanding cities, growing populations, and increasing demand for land would create ongoing challenges. Careful planning, scientific research, and respect for nature would remain essential parts of everyday life as people continued sharing the planet with the ancient animals that had never disappeared. Long before human beings appeared, Earth's climate was always changing. Some changes happened slowly over millions of years, while others happened much faster because of powerful natural events. If the prehistoric era had never ended, and the age of dinosaurs and other ancient life had continued, instead of giving way to the world we know today, Earth's climate would also have continued to change. The climate would not have stayed the same from one age to another. The movement of the continents, changes in the oceans, volcanic activity, the growth and loss of forests, and changes in the atmosphere would have continued to shape temperatures, rainfall, winds, and seasons across the planet. At the beginning of this endless prehistoric world, the climate would have remained much warmer than the climate that many parts of the modern world experience today. Large areas near the equator would have been hot throughout the year, while regions closer to the poles would have been much milder than they are today. Ice sheets would have been very small or completely absent in many periods. Snow would have fallen in some high mountains and in parts of the far north and south during colder seasons, but large frozen regions would have been uncommon for long periods of time. The atmosphere would have contained different amounts of gases over long stretches of time. Carbon dioxide released from volcanoes would have remained one of the most important gases affecting the climate. Volcanoes would have continued to release ash, steam, and gases into the sky. During times when volcanic activity became stronger, more carbon dioxide would have entered the atmosphere. This would slowly raise global temperatures over many thousands or even millions of years. Plants growing across forests, swamps, and open land would remove part of this carbon dioxide through photosynthesis, helping to balance some of the changes, although the balance would never remain exactly the same for very long. The oceans would also play an important part in controlling the climate. Warm ocean currents would carry heat from tropical regions toward cooler parts of the world. Cold currents would move cooler water back toward lower latitudes. As the continents slowly shifted because of the movement of Earth's crust, these currents would also change direction. A new mountain range rising from the ground, or a narrow sea opening between continents, could completely change the way ocean water moved around the world. These changes would slowly affect rainfall, temperatures, storms, and humidity across many regions. As millions of years passed, the continents would continue moving only a few centimeters each year. Although this movement would seem very slow during a human lifetime, it would completely reshape the planet over very long periods. Continents that were once separated by wide oceans could slowly move closer together. Others that were once connected could slowly drift apart. These movements would create new coastlines, close old seas, form new oceans, and build huge mountain ranges. Every one of these changes would influence Earth's climate. When mountain ranges rose higher into the sky, they would block moist air moving across the land. One side of a mountain range would receive heavy rainfall, while the other side would become much drier. Rivers would change direction, forests would spread into some places, and deserts would slowly appear in others. Animals and plants living in these regions would need to adapt to these changing conditions if they were to survive. Large forests covering much of the land would also help shape the climate. Ancient forests filled with conifers, ferns, cycads, ginkgo trees, and many other prehistoric plants would absorb large amounts of carbon dioxide from the atmosphere. They would also release water vapor into the air through their leaves. This moisture would help form clouds and rainfall over many regions. Areas with thick forests would often remain wetter than open landscapes with fewer plants. Sometimes enormous volcanic eruptions would cover wide areas with lava and thick layers of ash. During the first months or years after these eruptions, ash high in the atmosphere could block part of the sunlight reaching Earth's surface. This could temporarily cool some regions. As the ash slowly settled back to the ground, carbon dioxide released during the eruptions would continue building up in the atmosphere, leading to warmer conditions over much longer periods. Different regions would experience these changes in different ways, depending on their distance from the eruptions and the direction of global winds. The amount of rainfall would continue changing over time. Some periods would bring many years of heavy rain across large areas, allowing rivers to grow larger and wetlands to spread across the land. Lakes would fill with fresh water and plant life would become richer in many places. During other periods, rainfall would decrease, rivers would shrink, lakes would become smaller, and dry grasslands or deserts would replace forests in some regions. Animals would need to travel farther in search of food and water during these dry times. Strong storms would remain a natural part of this prehistoric Earth. Warm oceans would provide energy for powerful tropical storms. Coastal regions would sometimes experience heavy rain, strong winds, and flooding. Inland areas could also receive intense thunderstorms as warm, moist air met cooler air moving across the land. Lightning would frequently start natural fires in forests and grasslands. These fires would clear old vegetation and allow new plants to grow after the rains returned. The poles would also experience long periods of change. At certain times, the North and South polar regions might remain free from permanent ice. Forests could spread much farther toward the poles than they do today. Dinosaurs and many other prehistoric animals would be able to live in these higher latitudes because temperatures would remain much milder. During cooler periods, snow would last longer each year, and small glaciers could slowly grow in mountain valleys and colder regions. Earth's orbit around the Sun would continue changing over very long periods. Small natural changes in the shape of the orbit, the tilt of Earth's axis, and the direction of its axis would slightly change how sunlight reached different parts of the planet. These slow cycles would influence temperatures and rainfall over thousands of years. Some regions would become slightly warmer while others would become cooler. Wet seasons and dry seasons could also become stronger or weaker depending on these natural cycles. Ancient seas would remain full of life and marine organisms would also affect the climate. Tiny living organisms floating near the ocean surface would absorb carbon dioxide during their lives. When many of them died, their remains would sink to the sea floor, where some carbon would become trapped in sediments over very long periods. This natural process would slowly remove part of the carbon dioxide from the atmosphere. Wetlands and swamps would continue covering many low-lying regions. These wetlands would store large amounts of water during rainy seasons and slowly release it into rivers during drier periods. Thick plant material would collect in these wetlands year after year. Over millions of years, some of this material could become buried beneath layers of sediment. These natural processes would continue changing the balance of carbon stored in Earth's surface. As different groups of prehistoric plants evolved, they would gradually spread into new environments. Some species would become better at surviving dry weather, while others would remain dependent on warm, wet forests. The spread of these plants would influence soil, rainfall, and local temperatures. Areas covered with thick vegetation would remain cooler during the day than open rocky ground because plants would release moisture into the air. Dinosaurs themselves could also influence local environments. Huge plant-eating dinosaurs feeding across wide forests and plains would shape the growth of vegetation. Their movement would create open spaces where sunlight could reach the ground. Their waste would return nutrients to the soil. helping new plants grow. Meat-eating dinosaurs would help control the numbers of plant eaters, preventing some areas from being stripped of too much vegetation. These natural relationships would continue supporting healthy ecosystems that interacted with the climate. Over many millions of years, entirely new prehistoric species would appear, while others disappeared through natural evolution. Different animals would become better suited to changing temperatures, rainfall, and food supplies. Some would develop thicker coverings for cooler climates, while others would become better at surviving long dry seasons. Large migrations would occur whenever changing weather patterns altered the availability of food and water across the continents. As the continents continued moving, new inland regions would form far from the oceans. These places would receive less moisture because ocean winds would lose much of their water before reaching the interior. Such regions would slowly become dry, supporting different prehistoric plants and animals from those living near the coasts. Coastal regions would usually remain wetter because they would continue receiving moist air from the seas. Long periods of warm conditions could allow tropical forests to spread across enormous areas of land. Thick tree canopies would provide homes for countless insects, reptiles, amphibians, early birds, mammals, and many dinosaur species. Warm rivers flowing through these forests would support fish, turtles, crocodile relatives, and many other aquatic animals. During cooler ages, some of these forests would shrink, allowing open woodlands and grass-covered landscapes to expand into new regions. The climate would never remain completely stable. Slow natural changes inside Earth, changes in the atmosphere, shifting continents, evolving plant life, changing ocean currents, volcanic eruptions and natural cycles in Earth's orbit would continue working together across millions of years. Every generation of prehistoric plants and animals would experience slightly different weather from those that lived before them. Some ages would be warmer, others cooler. Some would be wetter, while others would become much drier. Rivers, lakes, forests, coastlines, mountains, and deserts would continue changing as Earth's climate slowly followed the changing conditions of the planet itself. After the early stages of dinosaur survival and their continued spread across land, sea margins and air spaces filled with different forms of flying reptiles and early birds, their bodies kept changing slowly over very long periods of time. These changes did not happen in a single moment, but over many generations, where small differences in size, shape, and behavior appeared in offspring and remained in those that survived longer and reproduced more. Over a long stretch of Earth history measured in millions upon millions of years, these small changes built up and formed new kinds of dinosaurs with different ways of living. Many dinosaur groups became adapted to living in very different environments. Some remained in open land areas where plants were low and scattered, while others lived in regions where tall plants were more common. The shape of their teeth changed in many species depending on what they could eat. Some developed teeth that were better for cutting plant material, while others had teeth that could handle tougher food materials. In some cases, teeth were replaced many times during life, allowing continuous feeding even when teeth were worn down or damaged. The body sizes of dinosaurs also changed across time. Some remained small with light bodies that allowed quick movement and easy hiding from larger predators. Others became very large and had heavy bodies, supported by strong bones and thick limbs. The structure of the bones in many species became hollow or partly hollow, which helped reduce weight while still maintaining strength. This allowed some dinosaurs to move with more energy efficiency across large distances in search of food or nesting places. skin covering in dinosaurs also varied widely. Many species had rough, scaly skin that protected them from environmental conditions and physical injury. In some groups, evidence shows that feather-like coverings appeared, especially in smaller species and those related to early birds. These coverings may have helped with temperature control in different climates, especially during times when daily temperatures changed between warm and cool conditions. Over time, these coverings became more complex in certain lineages, spreading across more parts of the body in some species. Reproduction played an important role in their continued survival. Dinosaurs laid eggs, and many species created nests in different ways. Some laid eggs in shallow ground nests, while others placed them in carefully prepared areas using plant material and soil. In several fossil discoveries, groups of eggs have been found together, showing that some dinosaurs returned to the same areas repeatedly to lay eggs. The eggs themselves varied in size and shell thickness, depending on the species and environment. Some shells were thin to allow easier gas exchange, while others were thicker to provide more protection. The young dinosaurs that came out of these eggs often had to survive in environments filled with predators and changing conditions. In some species, young dinosaurs grew quickly, reaching larger sizes in a short time. In others, growth was slower but still steady over many years. Bone growth patterns show that many dinosaurs had growth rings, which helps scientists understand how their bodies developed over time. These rings show periods of faster growth and slower growth depending on food, availability, and environmental conditions. The nervous system of dinosaurs also became more developed in many groups. Brain size relative to body size increased in some species, especially those that needed quick reactions for hunting or escaping danger. The structure of the inner ear in some species suggests that balance and movement coordination improved over time, allowing smoother motion during walking or running. These features helped many dinosaurs survive in environments where quick responses were necessary. Feeding behavior among dinosaurs became highly diverse. Herbivorous dinosaurs developed ways to process large amounts of plant material. Some had wide mouths and strong jaws that allowed them to crop vegetation quickly. Others had narrow mouths that were used to select specific plant parts. In some species, food was processed in the stomach with the help of swallowed stones that helped grind plant matter. Carnivorous dinosaurs developed strong jaws and sharp teeth that allowed them to capture and consume other animals. Some species hunted alone, while others may have moved in groups when searching for food. As time passed, many ecosystems where dinosaurs lived changed slowly. Plant life evolved and shifted, leading to new food sources. Forest-like environments became more widespread in some regions, while open areas remained in others. These changes in plant distribution influenced where different dinosaur species could live. Some moved into new areas to follow food sources, while others adapted to the existing vegetation in their surroundings. The air above dinosaur habitats also became increasingly active with flying reptiles and early birds. These flying creatures occupied different levels of the sky, some feeding on insects, others on fish, and some possibly on small animals. The presence of flying life added another layer to the environment, influencing how dinosaurs on the ground behaved. Some dinosaurs may have developed awareness of movement above them, adjusting their feeding and resting behavior in response to airborne activity. Water environments were also important in dinosaur survival. Rivers, lakes, and coastal regions supported many species that fed near or within water. Some dinosaurs were able to wade into shallow waters to find food, while others stayed on land but depended on water sources nearby. Fish, small aquatic animals and plants growing near water edges formed part of the food chain that supported many different life forms. The climate of Earth continued to shift over long periods. Temperatures changed slowly, and rainfall patterns varied across regions. Some areas became more humid with dense plant growth, while others became drier, with more open landscapes. Dinosaurs adjusted to these conditions through gradual changes in their body structure, behavior, and life cycles. Skin coverings, body size, and feeding habits all played roles in how well they could live in different conditions. Social behavior in some dinosaur groups may have developed in different ways. Evidence from fossil trackways shows that some dinosaurs moved in the same direction at the same time, suggesting movement in groups. Other evidence shows that some species may have lived more independently. The level of interaction between individuals likely depended on species type, environmental pressure, and availability of resources. Communication between dinosaurs is still understood only through indirect evidence. Some species had crests or hollow structures in their skulls that may have been used for sound production. Others may have used body movement or visual signals. These features likely helped them interact during feeding, reproduction, or movement through shared spaces. As generations continued over long spans of time, new forms of dinosaurs appeared while older forms disappeared. This ongoing change was not sudden but occurred gradually across different regions of Earth. Fossil records show patterns of appearance and disappearance that reflect these long changes in life forms. Different groups of dinosaurs occupied different ecological roles depending on their physical features and behavior. The structure of dinosaur limbs also changed in many lineages. Some developed stronger hind limbs for faster movement, while others had limbs designed for supporting heavy body weight. In certain species, forelimbs became smaller or specialized for particular functions such as grasping or balance. The arrangement of joints and muscles in these limbs allowed a wide range of movement types depending on the species. Respiratory systems in many dinosaurs were highly efficient. Airflow through their bodies was supported by complex lung structures that allowed continuous oxygen movement. This helped sustain larger body sizes and higher activity levels in some groups. The efficiency of breathing systems also supported growth and reproduction over long periods of life. The skin, bones, muscles, and internal systems of dinosaurs all worked together to support survival in changing environments. These biological systems continued to adjust slowly as environmental conditions shifted over time. The long history of dinosaur life shows continuous development of new traits, behaviors, and physical structures without interruption in their presence across Earth's surface. The evolution of mammals during the long time when dinosaurs ruled the land began in a world that was already shaped by earlier waves of life. The land was filled with large reptiles, belonging to groups that included Dinosauria, and these animals occupied many ecological roles across forests, plains, river systems, and coastal regions. The early ancestors of mammals existed in this same world, and they belonged to a group of vertebrate animals that had already developed basic features such as a backbone, a skull, and limbs that supported movement on land. These early mammal ancestors were part of a long biological line that eventually led to modern mammals. The origin of mammals can be traced to a group of animals known as synapsids, which appeared long before true mammals became established. Synapsids were part of early land vertebrates that lived during a time when the planet was recovering from earlier mass extinction events. Over long periods of time, some synapsids developed features that became more similar to those seen in mammals. These features included changes in the skull, changes in jaw structure, and changes in how food was processed inside the mouth. These changes happened gradually across many generations. During the time when dinosaurs became the dominant land animals, early mammal relatives had already spread into many environments. These environments included dense vegetation areas, open ground regions, underground spaces, and forest floors. Many of these early mammals were small in body size and had body structures that allowed them to move through narrow spaces. Their small size played a role in how they survived in ecosystems that were dominated by large reptiles belonging to Dinosauria. The early mammals had a body covering made of hair. Hair played a role in regulating body temperature. This feature allowed these animals to maintain activity during different environmental conditions. Alongside hair, early mammals also developed glands in the skin that produced substances used for different biological purposes. These glands became part of the biological systems that supported survival in changing environments. The skeletal structure of early mammals continued to change over long periods of time. The bones of the jaw became more specialized. In earlier synapsids, several bones were involved in the jaw joint. Over time, some of these bones became part of the middle ear structure in mammals. This change allowed sound transmission to improve within the ear. The development of the 3 small ear bones became a defining feature of mammals. The teeth of early mammals also developed specialized forms. Different types of teeth appeared in the mouth, including teeth used for cutting, tearing, and grinding food. This differentiation of teeth allowed early mammals to process a wider range of food materials. The structure of teeth became more complex, and tooth replacement patterns also changed over time. These changes allowed feeding habits to become more efficient in different environments. The nervous system of early mammals also developed more complexity. The brain increased in relative size within the skull over long periods of time. This change supported improved sensory processing. Smell became an important sense, and the nasal region of the skull developed structures that increased the surface area for detecting airborne chemical signals. These signals were used to locate food sources, detect other animals, and respond to environmental changes. During the period when dinosaurs, such as Tyrannosaurus rex and Triceratops, existed in later geological times, mammals had already diversified into several small-bodied groups. These groups included animals that lived in trees, animals that lived underground, and animals that lived near water sources. Each group developed biological traits that matched the conditions of their environments. Reproduction in early mammals involved internal development of embryos. In many early forms, young were born at a relatively early stage of development. Some groups developed structures for feeding young through specialized skin glands. These glands produced nutrient-rich substances that supported early growth. This reproductive strategy supported survival in environments where eggs laid on open ground faced many environmental risks. The skin of early mammals developed layers that provided protection from environmental exposure. These layers helped reduce water loss and supported survival in dry or variable climates. The structure of the skin also played a role in temperature regulation. The presence of hair increased the ability to retain heat during cooler conditions and reduce overheating during active periods. Early mammals lived in ecosystems where many niches were already occupied by large reptiles belonging to Dinosauria. These ecosystems included forest systems filled with conifer trees, fern-like plants, and early flowering plants that appeared later in geological time. Plant diversity influenced the availability of food sources for herbivorous reptiles, and also influenced the availability of insects and other small organisms that early mammals fed on. Insect populations became an important food source for many early mammals. Insects provided a steady supply of protein and nutrients. Early mammals developed sensory systems that allowed them to detect movement and vibrations in their environment. These systems included sensitive whisker-like hairs that responded to touch and air movement. These features supported nocturnal activity patterns in many species. Nocturnal activity allowed early mammals to remain active during times when larger reptiles were less active. This pattern of activity involved movement through forest floors, underground burrows, and sheltered environments. The ability to remain active during nighttime hours supported access to food sources and reduced direct encounters with large predators belonging to Dinosauria. The development of the diaphragm muscle in mammals allowed more efficient breathing. This muscle separated the chest cavity from the abdominal cavity and supported lung expansion. Improved breathing efficiency allowed sustained activity over longer periods of time. This feature supported movement, foraging, and escape responses in environments filled with large reptiles. The circulatory system of early mammals also developed features that supported high metabolic activity. The heart became divided into chambers that separated oxygen-rich blood from oxygen-poor blood. This separation supported efficient oxygen delivery to body tissues. The ability to maintain stable internal body conditions supported activity in different environmental conditions. The fossil record shows that early mammals existed alongside many dinosaur groups across different geological periods. These mammals left behind remains such as teeth, jaw fragments, and bone structures. Teeth fossils are especially important because they preserve detailed patterns of diet and feeding behavior. The shape and wear patterns of teeth provide information about the types of food consumed. Some early mammal groups developed adaptations for climbing. These adaptations included curved claws and flexible joints. These features supported movement along tree trunks and branches. Forest environments provided shelter and food resources, including insects and plant material. Tree-based living also reduced exposure to ground-dwelling predators belonging to Dinosauria. Other mammal groups developed adaptations for digging. These animals had strong forelimbs and robust claws. Burrowing behavior allowed access to underground spaces where temperature and humidity conditions remained more stable. Underground living also provided protection from surface conditions and predators. These burrows often contain nests and food storage areas. The sensory development of early mammals included improvements in hearing. The middle ear bones allowed vibration detection from air and ground sources. This improvement supported awareness of environmental movement and distant sounds. The inner ear structures also contributed to balance and spatial orientation during movement. The digestive systems of early mammals became adapted to different types of food sources. Some mammals developed digestive tracts suited for insect consumption. Others developed systems that allowed processing of plant material. The development of different gut structures supported dietary diversity across mammal groups. During later geological periods, flowering plants became more widespread. These plants produced seeds, fruits, and other structures that provided new food sources. Early mammals interacted with these plant systems by feeding on seeds and small plant parts. These interactions contributed to changes in feeding behavior and digestive adaptations. The growth patterns of early mammals involved stages of rapid development after birth. Young mammals received care from adults in many species. This care included feeding, protection, and shelter provision. Parental care increased survival rates during early life stages. The skin glands of mammals became more specialized over time. Some glands produced oils that helped maintain skin and hair condition. Other glands produced chemical signals used for communication between individuals. These chemical signals played a role in reproduction and social interaction. The brain development of mammals included expansion of regions responsible for smell and sensory integration. The cerebral structure became more complex, supporting learning and memory functions. These changes allowed mammals to respond to environmental patterns and resource availability. The locomotion of early mammals involved varied movement styles. Some species used rapid running movements across ground surfaces. Others used climbing movements in forest environments. Some species moved through water environments, using limbs for swimming. Each movement style matched environmental conditions and resource availability. The distribution of mammals across landmasses was influenced by the arrangement of continents during the time of Dinosauria dominance. Land connections allowed movement between regions. Geographic separation influenced the development of distinct mammal groups in different areas. Some early mammals developed gliding abilities. These animals had skin extensions between limbs that allowed controlled movement through the air between trees. This movement allowed access to food sources in different parts of forest environments. It also allowed movement across gaps between trees. The metabolic rate of mammals remained consistently active. This supported continuous energy use and required regular food intake. Feeding behavior was therefore frequent in many species. Small body size supported lower absolute energy requirements while maintaining active lifestyles. The interaction between mammals and dinosaurs included indirect relationships involving shared environments. Mammals occupied ecological roles that included insect consumption and small organism predation. These roles contributed to ecological balance within ecosystems dominated by Dinosauria. The fossil evidence of mammal evolution includes preserved teeth with complex enamel patterns. These patterns show growth rings and wear structures that indicate feeding behavior over time. Jaw fragments show muscle attachment points that reveal chewing strength and movement patterns. The evolutionary changes in mammals continued across long geological time spans. Small variations in anatomy accumulated across many generations. These variations included changes in limb structure, skull shape, and sensory organs. Over time, these changes produced a wide range of mammal forms, adapted to different ecological roles. The environment in which mammals evolved under dinosaur dominance included changing climates, shifting vegetation patterns, and geological activity. These environmental conditions influenced the distribution of both mammals and dinosaurs across landscapes. The presence of Dinosauria remained dominant in many regions, while mammals continued to occupy smaller ecological niches. The early mammal body plan remained relatively small in many groups. This small size allowed movement through complex terrain, including leaf litter, roots, and underground spaces. These environments provided food sources and shelter. Movement patterns included quick bursts of activity and periods of rest within protected spaces. The development of sensory whiskers allowed mammals to detect changes in airflow and surface contact. These sensory structures played a role in navigation within low-light environments. The integration of sensory information supported decision-making during movement and feeding. The reproductive cycles of mammals became more regulated over time. Seasonal changes influenced breeding periods. Environmental conditions influenced the timing of birth and growth. These cycles aligned with food availability and environmental stability. The continued development of mammalian features occurred while large reptiles belonging to Dinosauria remained the dominant vertebrates on land. mammals maintained diverse biological adaptations that allowed survival across multiple environmental conditions. These adaptations continue to accumulate across long periods of evolutionary time, shaping body structures, sensory systems, reproductive patterns, and ecological roles, while dinosaur-dominated ecosystems remained active across land, forest, and river environments. The continents in a never-ending prehistoric world exist in forms shaped by constant movement of land, water, and heat from within the Earth. Large land areas stretch across wide distances, filled with many kinds of surface features. Some regions hold long plains covered in thick layers of soil formed over long periods. Some regions hold high ground formed by slow rising of the Earth's surface. Other regions hold broken ground where the land has split and shifted, forming deep cracks and uneven surfaces. The edges of land areas often change shape due to ongoing movement beneath the surface. These changes continue without stopping, shaping the arrangement of land over time. The land areas contain many environments that support living things. Forest regions spread across large sections of land. These forests contain dense plant life with tall tree forms, thick ground plants, and wide plant groups that cover the soil. Open land areas also exist, filled with grasses and low vegetation that grow in wide spreads. Wet regions form in many places where water collects on the surface. These wet regions include shallow water zones, muddy grounds, and areas with slow water flow. Dry regions also appear where rainfall is limited, leading to ground that holds little plant growth. Each type of land area changes slowly due to water flow, wind movement, and changes in the ground beneath. Oceans cover a large portion of the planet in this prehistoric world. These oceans hold deep water zones and shallow water zones. Deep water zones contain thick layers of water that extend far below the surface. Shallow water zones exist near land areas, where sunlight reaches the bottom layers of water. Ocean floors hold many forms of ground structure, including flat surfaces, raised ridges, and deep openings. These structures form through continuous movement of the Earth's crust beneath the water. Ocean water moves in steady patterns influenced by wind, temperature changes, and Earth rotation. Large movements of water travel across long distances, spreading warmth and minerals. Smaller movements occur near coastlines where land and water meet. These movements shape the flow of nutrients and support life forms in the water. The water contains many dissolved materials that come from land erosion and underwater activity. Land near oceans forms coastal regions. These coastal regions include wide beaches made of sand and small rock fragments. Some coastal regions contain steep rock edges where land rises sharply from the water. Other coastal regions contain flat land that extends slowly into the water. These coastal areas change shape over time due to the movement of water and sediment. Sediment moves from rivers and land erosion into the ocean, forming new layers along the shore. Rivers extend from inland regions toward the oceans and seas. These rivers carry water from rainfall, underground sources, and melting surface ice in colder regions of the planet. River paths move through many types of land. Some river paths pass through forest regions, while others pass through open land and dry regions. River channels shift slowly due to erosion of soil and rock. Over long periods, river paths create wide valleys and deep channels. Lakes form in areas where water collects in natural ground depressions. These lakes vary in size and depth. Some lakes contain fresh water that flows from rivers and underground springs. Other lakes hold water that becomes more concentrated with dissolved materials due to evaporation. Lake surfaces change with wind movement, rainfall, and inflow from rivers. Surrounding lake areas often develop thick plant growth due to constant water availability. Underground water systems exist beneath land areas. These systems contain water stored in porous rock layers and soil spaces. Water moves slowly through these underground systems, connecting with rivers, lakes, and oceans. Underground water plays a major role in maintaining moisture in soil and supporting plant life in many regions. In some places, underground water reaches the surface through natural openings, forming springs that feed into rivers and lakes. The atmosphere above the continents and oceans contains layers of gases that support weather activity. Clouds form in many regions when water vapor rises and cools. These clouds move across land and ocean surfaces, carrying moisture from one region to another. Rainfall occurs when clouds release water droplets, returning moisture to the surface. Rainfall patterns vary across the planet, creating regions with frequent moisture and regions with limited moisture. Wind moves across land and ocean surfaces due to differences in temperature and pressure in the atmosphere. These wind movements carry dust, moisture, and seeds from plants across large distances. Wind shapes land surfaces by moving small particles of soil and sand. Over time, wind activity changes the texture and form of exposed ground areas. Volcanic activity occurs in many regions of the planet. Magma rises from deep inside the Earth and reaches the surface through openings in the crust. When magma reaches the surface, it forms lava flows that spread across land. These flows create new layers of rock as they cool and harden. Volcanic regions often contain uneven ground, cracks, and openings where heat and gases escape. These regions also influence nearby land and water systems by adding minerals and heat. Mountain regions form through movement of the Earth's crust. Large sections of land shift and create raised structures that extend across long distances. These mountain regions contain steep slopes, narrow valleys, and rocky surfaces. Erosion from wind and water slowly changes the shape of these mountains over time. Rivers often begin in mountain regions and flow downward toward lower land areas. Plains stretch across large sections of land in many parts of the prehistoric world. These plains contain relatively flat ground, with soil layers that support plant growth. Sediment carried by rivers often spreads across plains, forming new soil layers. Plains often connect to other land areas such as forest regions and dry regions. The surface of plains changes slowly due to wind, water, and biological activity in the soil. Desert regions exist in areas with limited water availability. These regions contain dry soil, rock surfaces, and sand deposits. Temperature changes in desert regions occur between daytime and nighttime periods, affecting the condition of the ground surface. Wind movement shapes the sand and dust in these regions, creating shifting surface patterns. Some desert regions contain underground water sources that support limited plant life. Polar regions exist in areas with low temperatures and long periods of reduced sunlight. These regions contain ice formations, frozen ground, and cold water zones. Ice layers form over land and water surfaces, shaping the structure of the ground beneath. Seasonal changes affect the extent of ice coverage, with expansion and reduction occurring over time. Some plant and animal life exists in these regions, adapted to cold conditions and limited resources. Coastal oceans contain shallow water zones with strong interaction between land and water. These regions support movement of nutrients between land and sea. Sediment from rivers spreads into coastal water, forming layers on the ocean floor. These layers influence the shape of underwater ground structures. coastal waters also experience changes in temperature and salinity due to freshwater input from rivers. Deep ocean regions contain large water volumes with limited light penetration. The ocean floor in these regions contains ridges, basins and openings formed by Earth movement. Heat from beneath the Earth influences water conditions in some deep regions. Mineral deposits form in areas where underwater activity releases materials into the ocean water. Island regions exist in some ocean areas where land rises above the water surface. These islands form through volcanic activity or movement of Earth's crust. Islands contain many types of land environments, including forests, plains, and rocky areas. Water surrounds these land areas, influencing moisture levels and climate conditions. Some islands change shape over long periods due to erosion and volcanic activity. River delta regions form where rivers meet oceans or seas. These regions contain layers of sediment deposited by flowing water. The sediment spreads across wide areas, forming complex networks of channels and wetlands. Plant life grows in these regions due to high moisture and nutrient availability. The structure of river delta regions changes continuously due to water flow and sediment movement. Wetland regions exist in many parts of the continents. These regions contain waterlogged soil and slow-moving water. Wetlands support thick plant growth and serve as areas where water is filtered through natural processes. Water levels in wetlands change with rainfall, river flow, and seasonal patterns. The soil in wetlands contains high amounts of organic material from plant and animal remains. Ground beneath all land and ocean areas contains layers of rock formed over long periods. These layers store information about past environmental conditions. Movement within these rock layers causes changes on the surface, including shifts in land shape and formation of new geological structures. Heat from deep inside the Earth influences the movement of these layers and contributes to volcanic and tectonic activity. Air circulation patterns move heat and moisture across continents and oceans. These patterns influence rainfall distribution and temperature conditions in different regions. Some areas receive frequent moisture from ocean air movement, while other areas receive limited moisture due to distance from water sources. These circulation patterns remain active across the entire planet's surface. Living systems interact with land, water, and air across all regions. Plant life grows in areas with sufficient water and nutrients. Animal life moves across land, water, and air environments, adapting to available resources. Microorganisms exist in soil, water, and underground spaces, contributing to nutrient cycles and decomposition processes. These living systems interact continuously with environmental conditions. Sediment movement occurs through water flow, wind activity, and gravity. Sediment includes small rock particles, soil fragments, and organic material. This material moves from high ground to low ground areas and collects in riverbeds, lakes, and ocean floors. Over time, sediment layers form thick deposits that influence land and water structures. Surface conditions of continents and oceans change due to continuous Earth activity. Land rises in some regions and lowers in others due to movement beneath the surface. Water levels shift due to changes in climate and geological activity. These ongoing processes shape the arrangement of continents, oceans, and landscapes across the planet's surface. Water movement across the planet continues through connected systems that link rivers, lakes, underground water, oceans, and atmospheric moisture. Water from ocean surfaces rises into the air as vapor when heated by sunlight. This vapor moves upward and mixes with air layers at different heights. As it moves, It cools and forms small droplets that gather into cloud masses. These cloud masses travel across continents and oceans, carrying moisture far from where it first formed. When conditions change, the droplets return to the surface as rainfall, snow, or other forms of water release depending on temperature in each region. Rainfall reaches the ground and enters many pathways. Some of it flows across the surface into streams that join larger rivers. Some of it sinks into the soil, filling empty spaces between grains of rock and earth. Some of it collects in natural low areas, forming temporary or permanent water bodies. In colder regions, water can remain frozen for long periods, forming solid layers that slowly change shape under pressure. In warmer regions, water moves more freely through soil and rock layers. Rivers continue to act as major carriers of water across continents. Their flow is shaped by gravity, land slope, and the volume of water entering from rainfall and underground sources. River channels shift over time as flowing water removes soil and rock from their banks. This process creates new paths, while older paths may become dry or filled with sediment. Some rivers divide into many smaller branches near their ends, spreading water across wide, flat areas before reaching the ocean. The meeting points between rivers and oceans form zones where fresh water and salt water mix. These zones contain shifting patterns of water movement caused by tides, river flow, and wind activity. Sediment carried by rivers spreads into the ocean at these points, building new ground layers that extend outward from the land. Over time, these layers create broad, flat regions filled with many small water channels that divide and reconnect as water continues to move through them. Ocean systems remain active through large-scale water circulation. Water at the surface is influenced by wind that pushes it across long distances. These surface movements form flowing systems that transport heat and dissolved materials across the planet. Deeper water layers move more slowly but still shift due to differences in temperature and density. Water near the ocean floor interacts with underwater ridges and openings, where heat from inside the Earth affects local conditions. The floor of the ocean contains many forms of structure created by movement of Earth's crust. Some areas contain long raised formations that extend for great distances. Other areas contain deep hollow regions where the crust has moved apart. These changes occur over long periods as the Earth's surface slowly shifts. Sediment slowly collects on the ocean floor, covering older structures and forming new layers that record changes in water flow and material transport. Continental surfaces continue to experience steady transformation. Large land areas shift slowly in position, changing the arrangement of coastlines and interior regions. These movements can form new connections between land areas or separate existing ones. As land shifts, rivers adjust their paths, lakes change shape, and drainage systems reorganize. Some regions become more elevated, while others sink slightly lower, altering how water spreads across the surface. Soil layers across continents develop through the breakdown of rock and the accumulation of organic material. Rock breaks into smaller pieces due to temperature changes, water movement, and physical pressure. These fragments mix with decaying plant and animal matter, forming layers that support plant growth. Different regions develop different soil types depending on water availability, temperature conditions, and geological activity. Plant life spreads across continents wherever conditions allow growth. In regions with steady water supply, dense plant cover develops and spreads across large areas. In drier regions, plants grow in scattered patterns with wide spaces between them. Plant roots extend into the soil, stabilizing ground structures and influencing water movement beneath the surface. Plant material that dies and decays returns nutrients to the soil, maintaining continuous cycles of growth and breakdown. Animal life moves across land, water, and air environments. Some animals remain in specific regions where conditions remain stable. Others migrate between regions, following changes in water availability, temperature, and food sources. Animal movement influences the distribution of nutrients and seeds across land surfaces. Aquatic animal life occupies river systems, lakes, and ocean zones at different depths. Some organisms remain near the surface where sunlight reaches, while others live in deeper, dark zones. Microbial life exists in nearly all parts of the planet, including soil, water, rock layers, and underground spaces. These microscopic forms of life break down organic material and help recycle nutrients. They also interact with minerals in soil and rock, slowly changing the composition of underground layers. Their activity continues in both wet and dry environments, adapting to different conditions across the planet. Wind systems continue to shape surface conditions across continents. Wind carries small particles of dust and sand, moving them from one location to another. In open areas with limited plant cover, wind has a stronger effect on the ground surface. In areas with dense plant cover, wind movement is reduced near the ground. Over long periods, wind shapes hills, valleys, and flat regions by moving loose material and redistributing it across large distances. Temperature differences across the planet influence many natural processes. Warm regions experience higher rates of water evaporation, faster plant growth, and more active surface changes. Cold regions experience slower movement of water and slower biological activity. These temperature differences create distinct patterns in how landscapes develop and change over time. Volcanic regions continue to form new land surfaces. When magma rises to the surface, it spreads across land or water before cooling into solid rock. Repeated volcanic activity builds layers of new ground, gradually changing the shape of surrounding regions. Volcanic gases released during eruptions mix with the atmosphere and influence local air conditions. Ash from volcanic activity spreads across land and water, eventually settling into soil layers. Mountain systems continue to change through ongoing movement of Earth's crust. As land masses shift, pressure builds in certain regions, causing the ground to rise. These rising areas form long, elevated structures with steep slopes and narrow passages. Erosion from water and wind slowly reshapes these structures, removing material from higher areas and depositing it in lower regions. Plains continue to develop through the accumulation of sediment. Rivers carry material from higher ground and spread it across wide, flat regions. Over time, these layers build up and create smooth surfaces that extend across large areas. These regions often contain fertile soil that supports extensive plant growth. Desert regions continue to exist in areas with limited water input. Rainfall remains low and evaporation rates are high. Loose sand and dust move across the surface due to wind activity. Some desert regions contain rock formations shaped by long exposure to dry conditions and temperature changes between day and night. Polar regions continue to experience long periods of cold conditions. Ice covers large portions of land and water surfaces. Seasonal changes affect the extent of ice coverage, with some areas gaining or losing ice depending on temperature shifts. Beneath the ice, land and water systems continue to exist, slowly interacting with the frozen surface above. Island systems remain scattered across ocean areas. These land areas vary in size and elevation. Some islands are part of volcanic systems that continue to show activity, while others are shaped by slow movement of Earth's crust. Surrounding waters influence climate conditions on islands. affecting moisture levels and temperature stability. Wetlands continue to form in areas where water remains near the surface for long periods. These regions contain slow-moving water and saturated soil. Plant growth in wetlands is dense, and decomposition processes occur continuously, adding organic material to the soil. Water in wetlands moves slowly between surface areas and underground systems. Underground systems of water and rock continue to interact with surface environments. Water stored beneath the ground moves through rock layers and emerges in springs or feeds into rivers and lakes. These underground systems maintain moisture balance in many regions and support surface water systems during periods of low rainfall. Sediment movement continues across all environments. Material from rock breakdown, biological activity, and erosion travels through water, wind, and gravity. This material accumulates in low areas such as riverbeds, lake floors, and ocean basins. Over time, sediment layers become part of new ground formations. Air circulation systems continue to distribute heat and moisture around the planet. These systems move air masses between regions, influencing temperature and rainfall patterns. Changes in air movement affect cloud formation, storm development, and seasonal variations across continents and oceans. The interaction between land, water, air, and living systems remains constant across all regions of the planet's surface. Each system influences the others through continuous movement and exchange of materials. Water shapes land, land directs water flow, air distributes moisture and heat, and living systems respond to changes in all physical conditions. The fate of marine reptiles and ancient ocean life is a long story that spans many periods of Earth's history, where the oceans were filled with a wide range of living beings that developed, changed, and disappeared across very long stretches of time. These ocean worlds were not quiet or still. They held active systems of life where marine reptiles, early fish groups, shelled animals, soft-bodied creatures, and many other forms of life lived in waters that shifted in temperature, chemistry, and depth through millions of years. The history of these beings is closely tied to changes in sea levels, movements of land, volcanic activity under the ocean floor, and shifts in climate that affected oxygen levels and nutrient supply in water. Over long spans of time, these conditions shaped which groups of organisms could continue and which groups gradually ended. Marine reptiles first became prominent during the time when life on land was also expanding in many directions. Some reptiles that lived on land gradually adapted to life in water. These changes happened over long periods through gradual modifications in body structure that allowed movement in water, breathing at the surface, and feeding on ocean life. Among these marine reptiles were ichthyosaurs, plesiosaurs, and later mosasaurs. Each group developed its own way of living in the ocean environment. Ichthyosaurs developed streamlined bodies that allowed movement through water with strong tail motion. Their fossils show features that suggest active swimming habits and feeding on marine organisms. They appeared in early forms during the time after major biological recoveries following earlier extinction events and continued for many millions of years before their disappearance. Plesiosaurs developed different body structures that included long necks in many forms and broad bodies with limbs shaped for movement in water. Their fossils appear in marine sediments that once formed deep and shallow sea environments. These animals lived during long intervals of changing ocean conditions, where sea levels rose and fell across wide regions of the planet. Their presence in fossil records shows that they were widely distributed across ocean environments that existed at different times. They interacted with other marine life such as fish, ammonite groups, and early marine reptiles that shared similar habitats. Mosasaurs appeared later in Earth's history and became dominant marine reptiles in the final part of the Age of Reptiles in ocean systems. They developed from land-based ancestors that returned to ocean environments. Their bodies show adaptations for powerful swimming and feeding in marine ecosystems. Fossil evidence shows that they lived in seas that covered large areas of continental regions during periods when global sea levels were high. Their presence is found in many marine sediment layers that also contain remains of fish, marine turtles, and shelled organisms. Alongside marine reptiles, ancient ocean life included many other groups that played important roles in marine ecosystems. Ammonites were shelled organisms that lived in spiral shells and moved through ocean waters using buoyancy control. Their shells are found in large numbers in sediment layers from different geological periods. These organisms existed in many forms across long stretches of time and are used to identify different ages of rock layers due to their wide presence in marine deposits. Their life cycles involved growth within shells that were gradually expanded as the organism developed. Other shelled organisms included bivalves and gastropods that lived on seafloors or moved slowly through marine environments. These organisms contributed to the structure of ocean ecosystems by participating in nutrient cycles and forming part of the food supply for marine reptiles and fish. Coral organisms also formed reef structures in shallow marine environments. These reef systems created habitats that supported many forms of marine life and provided stable areas where organisms could live and reproduce. Reef systems changed across time due to environmental shifts in ocean chemistry and temperature, which affected their development and distribution. Fish groups also played an important role in ancient oceans. Early fish developed a range of body forms and feeding methods that allowed them to occupy many ecological roles in marine environments. Some fish lived in deep water environments where light was limited, while others lived near the surface where light conditions supported different feeding patterns. The fossil record shows a wide range of fish forms preserved in marine sediments that formed under different environmental conditions. These fish served as food sources for marine reptiles and other predators in ocean systems. Ancient oceans were not stable environments. They changed through long cycles of geological and environmental activity. Volcanic eruptions under the seafloor released gases and heat that affected ocean chemistry. These changes could influence oxygen levels in water, which in turn affected marine life. Ocean currents shifted over time due to movements of Earth's crust, which changed the distribution of nutrients and temperature patterns in marine environments. Sea levels also changed repeatedly, covering land areas at times and retreating at others, which altered the shape and extent of marine habitats. Marine reptiles lived through these changing conditions for long periods. Their survival depended on their ability to adapt to changes in food availability, water temperature, and habitat structure. Some groups expanded during periods when marine ecosystems provided abundant food sources. Other groups declined when environmental conditions changed in ways that affected their ability to find food or reproduce successfully. Fossil records show patterns of appearance and disappearance that reflect these environmental changes over time. Ichthyosaurs eventually disappeared from the fossil record after a long presence in marine ecosystems. Their extinction occurred during a time of significant environmental change in ocean systems. The reasons for their disappearance are connected to shifts in marine food chains and changes in ocean conditions that affected their survival. Their absence marks the end of a long evolutionary line of marine reptiles that had existed through many periods of Earth's history. Plesiosaurs also disappeared after a long duration in marine environments. Their fossil record shows a gradual reduction in diversity leading up to their final absence. Changes in ocean ecosystems influenced their survival, including shifts in the types of fish and other marine organisms available as food sources. Environmental changes also affected breeding and habitat conditions in marine regions where they once lived. Mosasaurs disappeared at a later stage during a major transition in Earth's biological history. Their absence marks the end of the dominance of large marine reptiles in ocean ecosystems. Their extinction is recorded in marine sediment layers that also show changes in many other forms of life, including ammonites and various fish groups. After their disappearance, marine ecosystems continued with different groups of organisms taking on ecological roles that had once been filled by marine reptiles. Ammonites also disappeared in the same broad interval of time. Their extinction left a gap in marine ecosystems where they had once been widely present. Their shells remain preserved in large numbers within sediment layers, showing that they were once an abundant part of ocean life. Their disappearance is linked to widespread changes in ocean conditions and disruptions in marine food chains. After these events, ocean life continued with surviving groups of marine organisms that had lived alongside marine reptiles and ammonites. Fish groups continued to develop in new directions, and marine mammals later appeared and began to occupy many ecological roles in ocean environments. Coral systems continued to form in suitable marine areas, supporting a wide range of ocean life. Mollusks and crustaceans also continued their presence in marine ecosystems, adapting to new environmental conditions. Marine sediments from different time periods preserve a record of these changes. Layers of rock formed from ancient seabeds contain fossils of marine reptiles, fish, shelled organisms, and other ocean life forms. These layers show sequences of life forms that existed in different intervals of Earth's history. The chemical composition of these sediments also provides information about ocean conditions at different times, including oxygen levels, temperature ranges, and nutrient availability. Ocean environments in ancient times were influenced by the configuration of continents and the shape of ocean basins. As land masses shifted due to tectonic activity, ocean currents changed direction and strength. These changes influenced the distribution of marine life across different regions of the planet. Some marine reptiles occupied shallow inland seas that formed when ocean water covered low-lying land areas. Other organisms lived in deeper ocean regions where conditions remained different from coastal environments. The feeding behavior of marine reptiles involved capturing fish and other marine organisms. Ichthyosaurs used fast swimming motion to capture prey in open water environments. Plesiosaurs used neck movement and body positioning to approach prey in marine settings. Mosasaurs used strong jaws and body movement to capture a wide range of marine organisms. These feeding patterns are inferred from fossil structures, such as teeth shape, jaw formation, and body design preserved in rock layers. Reproduction in marine reptiles involved life cycles that took place in marine environments. Some ichthyosaurs show fossil evidence that suggests live birth in water. This adaptation allowed them to remain in ocean environments without returning to land for reproduction. Other marine reptiles show different reproductive strategies that are interpreted from fossil evidence and anatomical features preserved in skeletal remains. Ancient ocean life also included microorganisms that form the base of marine food systems. These microscopic organisms played roles in nutrient cycles and oxygen production in marine environments. Their presence influenced the survival of larger marine organisms, including reptiles and fish. Changes in their populations affected the entire structure of ocean ecosystems across long periods. Sedimentary rock formations preserve evidence of ancient ocean floors where marine reptiles once lived. These rocks contain traces of biological activity, such as burrows, feeding marks, and preserved remains of organisms. Over long periods, these sediments were buried and transformed into rock layers that now provide information about past marine environments. The distribution of fossils within these layers helps reconstruct patterns of ocean life across different time periods. Marine ecosystems have also experienced periods of ecological stress caused by rapid environmental changes. These events affected oxygen levels in water and altered food availability. Marine reptiles and other organisms responded to these changes through shifts in population size and distribution. Some regions of the oceans became less suitable for life during these periods, while other regions remained stable for longer intervals. The disappearance of marine reptiles marked a major transition in ocean ecosystems. After their absence, marine environments continued with new dominant groups of organisms. Fish diversity expanded in many directions, and marine mammals developed later and occupied ecological roles in ocean systems. Coral reefs continued to form and support marine biodiversity. Mollusks, crustaceans, and other invertebrate groups remained important parts of marine ecosystems. The fossil record continues to provide information about these ancient ocean systems. Each layer of sediment holds remains of organisms that lived during specific periods of Earth's history. These records show sequences of life forms that existed across long intervals of time. The structure of these records reveals patterns of emergence, persistence, and disappearance of marine reptiles and other ocean life forms. Marine reptiles and ancient ocean life represent a long history of biological development in ocean environments that changed repeatedly through time. Their presence is recorded in fossil remains, sediment layers, and geological formations that preserve evidence of life in ancient seas. The study of these remains continues to reveal details about ocean conditions, biological structures, and life processes that existed across extensive spans of Earth's history. Volcanoes, earthquakes, and geological activity through millions of years describe the long and ongoing movement and change of the Earth's outer layer and deeper parts. These processes have been active for a very long time, beginning from the early formation of the planet and continuing through all later periods of Earth history. The Earth has always had internal heat that moves upward from deep inside. This heat comes from the formation of the planet and from the decay of radioactive elements inside rocks. This internal heat causes movement in the rocky layers beneath the surface. These movements are responsible for volcanic eruptions, earthquakes, and the shifting of large sections of the crust. In the earliest stage of Earth history, when the planet was still forming and cooling, the surface was not stable. The outer layer was thin and constantly changing. Hot material from inside the Earth moved toward the surface. This movement caused repeated melting and solidification of rocks. At that time, volcanic activity was very frequent. Large amounts of gases and molten rock were released. These materials formed early crustal structures. Over long periods of time, the surface began to cool more, and solid rock layers started to become more stable in some regions, but movement inside the Earth continued. As time continued over hundreds of millions of years, the Earth developed a crust made of separate sections. These sections are called tectonic plates. These plates rest on a deeper layer that is partially soft and allows slow movement. The movement of these plates is caused by heat from inside the Earth. The plates move in different directions over long periods of time. When these plates move, they can interact in different ways. They can move toward each other, move away from each other, or move sideways. These movements are responsible for most volcanic activity and earthquakes. Volcanic activity occurs when molten rock from inside the Earth moves upward and reaches the surface. This molten rock is called magma, while it is underground. When it reaches the surface, it is called lava. The movement of magma happens when pressure builds inside the Earth. This pressure forces the molten material through cracks in the crust. These cracks are formed by tectonic movements. When magma reaches the surface, it can flow out slowly or it can be released in sudden and powerful eruptions. Over millions of years, repeated volcanic eruptions build new rock layers on the surface. Earthquakes occur when stress builds up inside the Earth's crust and is suddenly released. This stress is caused by the movement of tectonic plates. As plates move, they can become stuck at certain points due to friction. While they are stuck, pressure continues to build. When the pressure becomes too strong, the rocks break or shift suddenly. This sudden movement releases energy in the form of seismic waves. These waves travel through the ground and cause shaking on the surface. Earthquakes can happen at different depths inside the Earth, depending on where the movement occurs. Through millions of years, the Earth's surface has changed many times due to volcanic activity and earthquakes. Large landmasses have formed and broken apart. Mountain regions have formed where tectonic plates have pushed against each other. Ocean floors have changed as new crust formed and old crust was pushed back into the Earth. These processes happen slowly but continuously. Even when no major surface changes are visible in shorter periods of time, movement still continues beneath the surface. Volcanic activity has played an important role in forming the Earth's atmosphere and oceans. In early Earth history, volcanic eruptions released gases such as water vapor, carbon dioxide, and nitrogen. These gases gradually formed the early atmosphere. Water vapor condensed over time and formed oceans. This process took place over long periods of time as volcanic activity continued. Even in later stages of Earth history, volcanic eruptions continued to release gases that affected the atmosphere. Earthquakes have also influenced the structure of the Earth's surface. Repeated seismic activity can cause cracks, shifts, and changes in rock layers. Over long periods of time, these changes can affect the shape of land regions. Fault lines are formed where repeated movement occurs along fractures in the Earth's crust. These fault lines can remain active for millions of years. Along these lines, repeated earthquakes occur as stress builds and is released again and again. The movement of tectonic plates is slow but continuous. Over millions of years, this movement can cause large changes in the position of land and ocean areas. Some regions that were once connected become separated. Other regions that were once separated become connected. These changes happen through processes that include spreading at ocean ridges and sinking of crust in deep ocean areas. These processes are part of the long cycle of crust formation and destruction. Volcanic eruptions can occur in different forms depending on the type of magma and the conditions inside the Earth. Some eruptions release lava slowly, allowing it to flow over long distances before cooling and solidifying. Other eruptions release material suddenly, sending ash, gas, and rock fragments into the air. These different types of eruptions depend on the pressure, temperature, and composition of the magma. Over millions of years, repeated eruptions build volcanic mountains, lava plains, and other surface features. Earthquakes vary in strength depending on the amount of energy released. Some earthquakes involve small movements deep underground, while others involve large shifts in the crust. The energy release travels through different types of rock layers, and the movement can reach the surface in different ways. Seismic waves travel through solid rock and can change direction depending on the materials they pass through. Instruments placed on the surface record these waves and help identify the location and depth of the movement. The interaction between tectonic plates is a constant process. At some boundaries, plates move apart. When this happens, magma rises to fill the gap, forming new crust. This process often occurs under oceans where long underwater mountain systems form. At other boundaries, plates move toward each other. In these areas, one plate may move beneath another. This movement causes deep zones where material is pushed into the earth. It also causes volcanic activity and strong earthquakes. At sideways boundaries, plates slide past each other. This movement creates stress and results in repeated earthquakes. Over millions of years, volcanic and seismic activity has shaped many parts of the Earth's surface. Mountain ranges have formed in areas where plates collide. Ocean basins have formed and changed where plates move apart. Volcanic islands have formed in ocean regions where magma rises through weak points in the crust. These islands can grow over time through repeated eruptions. Earthquakes continue to affect these regions as plate movement continues. The interior of the Earth remains active due to heat flow from deeper layers. This heat moves slowly toward the surface and keeps the mantle in a semi-fluid state in some areas. This allows slow movement of rock material over long periods of time. This movement transfers energy and causes stress in the crust. When stress becomes too large, it is released through earthquakes or volcanic eruptions. This cycle continues without stopping. Rock layers inside the Earth record evidence of past volcanic and seismic activity. Layers of solidified lava show where eruptions occurred. Fractures and faults show where movement has taken place. Sediment layers can be disrupted by earthquakes, leaving signs of past seismic events. These records build a long history of Earth activity over millions of years. Volcanic gases released during eruptions also affect surface conditions. These gases include water vapor, carbon dioxide, sulfur compounds, and other elements. When released in large amounts, they can spread through the atmosphere. Over time, these gases become part of natural cycles that move between the Earth, oceans, and atmosphere. The release of gases has continued throughout Earth history. Earthquakes can also cause changes in water bodies. Movement of the seafloor can shift water above it. This can lead to changes in ocean levels in certain areas. On land, earthquakes can change the flow of rivers by shifting the ground surface. These changes can occur quickly during seismic events and then continue to affect water movement over time. Volcanic regions are often found in areas where tectonic activity is active. These regions can exist along plate boundaries or in areas where magma rises from deep inside the Earth. In some cases, volcanic activity occurs far from plate boundaries due to hot regions inside the mantle that allow magma to reach the surface. These hot regions remain in place while tectonic plates move over them, resulting in repeated volcanic activity in different locations over long periods. The process of crust formation and destruction continues as part of Earth's long geological cycle. New crust forms at spreading zones where magma rises and solidifies. Old crust is pushed back into the Earth at subduction zones where it melts and becomes part of the mantle again. This movement recycles materials over millions of years. Earthquakes and volcanic eruptions occur along these zones due to continuous stress and movement. Seismic activity also affects the stability of land surfaces. Repeated earthquakes can weaken rock structures and create zones of broken rock. These zones can extend over large areas and remain active for long periods. Movement along these zones continues whenever stress builds up again. This process repeats many times over geological time. Volcanic deposits found in rock layers show evidence of repeated eruptions over long periods. These deposits include solidified lava, ash layers, and other volcanic materials. Each layer represents a separate event in Earth history. Over millions of years, these layers accumulate and form thick sequences of volcanic rock. The movement of tectonic plates also influences the distribution of volcanic and earthquake activity across the planet. Certain regions experience frequent activity due to their location along plate boundaries. Other regions experience less frequent activity because they are located within stable plate interiors. However, even stable regions can experience occasional movement due to deeper processes inside the Earth. The energy inside the Earth continues to move through different layers. This energy is transferred through conduction and convection processes within solid and semi-solid materials. This movement causes slow changes in pressure and temperature conditions inside the Earth. These changes contribute to the movement of tectonic plates and the formation of volcanic and seismic activity. Over millions of years, the repeated action of earthquakes and volcanic eruptions has built and reshaped the Earth's surface continuously. New landforms have appeared and older ones have changed position or structure. These processes continue to operate today as part of the ongoing internal activity of the planet. Early humans lived in a prehistoric world filled with changing land, shifting climates, and many different living creatures. Their place in this world was shaped by the need to find food, find shelter, and stay alive in environments that were not stable or predictable. Human evolution took place over a very long time, involving many forms of early humans that appeared in different regions of the Earth. These early humans were part of the natural world and depended on it completely. Their survival was linked to their ability to use available resources in simple ways and to respond to changes in their surroundings. The Earth at that time had wide forests, open plains, dry regions, wet regions, and volcanic areas. Early humans lived in small groups and moved across landscapes in search of food and water. Their daily life required constant attention to the environment and careful use of natural materials. The earliest known human ancestors appeared millions of years ago in Africa. These early forms had bodies adapted for movement on the ground and hands that could hold and use objects. Over time, different groups of early humans developed. Some had stronger physical structures for walking long distances, while others had changes in skull shape that supported larger brains. These changes happened slowly over many generations. Early humans were not separate from other living beings in the environment. They shared land with large animals, smaller animals, birds, reptiles, and insects. Their place in the ecosystem was part of a long chain of survival, where each living thing depended on food sources from the environment. Early humans often relied on plants, fruits, seeds, and sometimes animal remains found in nature. Their diet changed depending on location and season. The use of simple tools marked an important part of early human life. Stones were shaped and used for cutting, breaking, and scraping. These tools were made from materials found in rivers, valleys, and rocky areas. Early humans learned through repeated actions how to select stones that could be shaped more easily. Over time, tool use became more organized, and different types of tools appeared for different tasks. Some tools were used for preparing food, while others were used for building simple shelters or for protection. The development of tools supported survival in different environments. Early humans carried tools with them as they moved from one area to another. The ability to use objects from nature for practical needs was an important part of their existence. Fire became a major element in early human life. At first, early humans may have used fire that occurred naturally from lightning strikes or volcanic activity. Later, they learned how to maintain fire for longer periods. Fire provided heat during cold conditions, light during dark hours, and a way to prepare food. Cooked food became easier to chew and digest. Fire also helped protect early human groups from certain animals. The control of fire required attention and shared responsibility within groups. Fire sites became central places where early humans gathered. These places supported communication, sharing of food, and group coordination. The presence of fire influenced movement patterns, since groups needed materials such as wood to maintain it. Early human groups were small and often consisted of family units. These groups moved together and shared tasks needed for survival. Cooperation was necessary for finding food, protecting young members, and responding to environmental changes. Communication within groups likely involved sounds, gestures, and simple forms of expression. Over time, communication became more structured, allowing better coordination during group activities. Early humans learned to observe animal behavior, track movement patterns, and understand seasonal changes. This knowledge was passed through repeated actions and shared experiences. Social life in early human groups was closely linked to survival needs, and every member had a role in daily activities. The environment of the prehistoric world changed across long periods of time. Some regions became colder, while others became warmer. Rainfall patterns changed, affecting plant growth and water availability. Early humans adapted by moving to new regions when resources became limited. Migration was not planned in a structured way, but happened through gradual movement over time. As groups moved, they encountered new types of landscapes and new living conditions. Some areas had dense vegetation, while others had open land with limited plant cover. Early humans adjusted their behavior based on these conditions. Their ability to move and adapt helped them survive across large regions of the Earth. Early human development included changes in physical structure and brain capacity. These changes supported improved coordination, memory, and problem-solving. Hands became more suited for precise movement, allowing better control of tools. The skull structure changed over long periods, supporting larger brain size. These changes did not happen quickly, but developed across many generations. Early humans with different physical traits lived at different times and in different regions. Some groups developed abilities that supported longer movement across land, while others developed skills for using tools in more advanced ways. These changes were part of natural development within human evolution. Food gathering was a central activity in early human life. Early humans collected plants, fruits, roots, and seeds from their surroundings. They also used simple hunting methods when possible, depending on available tools and group cooperation. Food sources changed with seasons, requiring movement and flexibility. Early humans needed knowledge of plant locations and animal movement patterns. This knowledge was shared within groups and passed through repeated experience. Food preparation involved basic processing methods, such as cutting, breaking, and sometimes cooking with fire. The availability of food influenced group size and movement patterns across landscapes. Shelter was another important part of early human survival. Early humans used natural formations such as caves, rock overhangs, and tree cover for protection. In some cases, they built simple structures using branches, leaves, and other natural materials. These shelters provided protection from weather conditions and animals. Shelter use changed depending on location and available resources. Groups often returned to familiar shelter sites when conditions were suitable. The construction of simple shelters required cooperation and shared effort within groups. Shelter sites also served as places for rest and group interaction. Early humans interacted with animals in many different ways. Some animals were used as food sources, while others were avoided due to danger. Early humans observed animal movement and behavior to understand their environment better. Animal remains sometimes provided materials such as bones or skins, which were used for practical needs. Early humans also competed with large predators for food resources. This interaction influenced movement patterns and group behavior. Knowledge of animal habits helped early humans survive in regions with many different species. The spread of early humans across different parts of the world happened over a long period of time. Starting from Africa, early human groups moved into parts of Asia, Europe, and other regions. This movement occurred gradually and followed available land routes. Different environments required different survival strategies. Early humans who moved into colder regions had to adjust to new conditions, while those in warmer regions adapted to different plant and animal life. This spread led to the presence of early human groups in many parts of the world. Each group developed ways of living suited to its surroundings. Language development in early human groups began with simple forms of communication. Sounds, gestures, and repeated signals were used to share information. Over time, these forms of communication became more structured. Early humans needed ways to share information about food sources, danger, and group movement. Communication helped improve coordination within groups. The development of more complex communication supported stronger group organization. This change happened slowly over many generations and was linked to brain development and social interaction. Human civilization in a land where dinosaurs still live begins in a world filled with constant biological activity, from very large reptiles and many smaller living creatures that move across land, water, and air. Humans appear as one group among many living beings, and they begin building ways of life that allow them to continue daily survival while sharing the same environment with dinosaurs. Early human groups live in small settlements made from wood, stone, and plant materials. These settlements are often placed in areas where large dinosaurs move less frequently, such as regions with thick forests, rocky ground, or high ground that is difficult for heavy animals to reach. Human groups learn early that movement patterns of dinosaurs change with seasons, rainfall, and plant growth, so human settlement patterns also change with these natural cycles. Food gathering becomes one of the most important parts of early human life. Humans collect fruits, seeds, roots, and other plant materials from safe areas. Hunting also takes place, but it is done with careful planning and group coordination. Humans focus on smaller animals for food, while avoiding direct conflict with large dinosaurs. In some regions, humans observe dinosaur feeding habits closely in order to understand when certain areas are safe to enter. Knowledge about animal movement is passed from older individuals to younger ones through spoken instruction and repeated practice. This knowledge becomes part of daily survival and affects how human groups organize their time and movement. Water sources play an important role in human settlement choices. Rivers, lakes, and natural springs attract both humans and dinosaurs. Because of this shared use of water areas, humans develop methods to approach water sources at times when large animals are less active nearby. Some human groups build simple barriers made from logs and stones near water collection points. These barriers do not block movement entirely, but provide limited separation between humans and large animals. Over time, humans develop observation routines where certain members of the group watch animal movement near water sources and signal safe periods for gathering water. Shelter building changes as humans adapt to living in a land filled with large animals. Structures are built with stronger supports and deeper foundations. In some areas, humans create shelters partly underground or within natural caves. Cave systems provide protection from environmental conditions and reduce exposure to large animal movement. Human settlements often include multiple exits, so that movement can continue if one direction becomes unsafe. Fire use becomes an important part of shelter life, providing light during night hours and helping with food preparation. Smoke from fires is managed carefully, so that it does not attract unwanted attention from large animals. Social organization within human groups becomes structured around shared safety responsibilities. Certain individuals focus on monitoring surroundings, while others focus on food preparation, shelter maintenance, and tool creation. Communication methods develop through sounds, hand signals, and written marks on stone or wood surfaces. These communication methods allow groups to respond quickly to changes in animal movement. Group decision-making often involves collective agreement on when to travel, when to remain in place, and when to move to another location. These decisions are influenced by seasonal changes and visible patterns of dinosaur activity across landscapes. Tool development advances as humans interact with their environment. Stone tools are shaped for cutting plants, preparing food, and defending against smaller threats. Wooden tools are used for digging and construction. Over time, humans begin combining different materials to create stronger tools. Bone materials from naturally deceased animals are also used for tool making. The presence of large dinosaurs influences the design of many tools, especially those used for protection and quick escape. Human toolmakers spend time observing animal movement and testing different shapes and edges for practical use in daily tasks. Agricultural practices begin in regions where dinosaur movement is less frequent or more predictable. Humans clear small areas of land and plant seeds for crops such as grains, vegetables, and fibrous plants. These cultivated areas are often surrounded by natural boundaries such as rivers or dense vegetation to reduce intrusion from large animals. Human groups assign members to monitor fields during growth periods. Crops are harvested in short cycles, and storage systems are created using pits, containers, and elevated platforms. Food storage becomes essential during periods when travel outside settlements becomes limited due to increased animal movement. Trade between human groups develops slowly. Groups exchange plant materials, stone tools, dried food, and crafted items. Travel routes are selected based on known patterns of dinosaur movement. Paths that remain relatively safe are used repeatedly, and markers are placed along these routes using stones, wood carvings, or painted symbols. Trade gatherings take place in areas where natural visibility allows early detection of approaching large animals. These gatherings are organized with structured timing so that groups can arrive, exchange goods, and leave within planned time periods. Education within human communities focuses on survival knowledge. Younger individuals learn how to identify plant types, animal tracks, weather changes, and safe travel routes. Learning is often practical, involving direct participation in daily tasks. Storytelling is used to preserve information about past encounters with large animals and environmental changes. These stories are not symbolic but serve as records of observed events and learned responses. Skills are passed through repetition and guided practice within each community group. As human populations grow in certain regions, settlement areas expand into more complex arrangements. Some settlements include multiple clustered living spaces connected by paths and shared resource areas. Storage locations are built separately from living spaces to reduce risk from animal intrusion. Defensive planning becomes part of settlement design, with watchpoints placed at higher positions to observe surrounding land. Movement within settlements follows defined paths that reduce exposure to open ground. Interaction with dinosaurs remains a constant part of life. Humans observe different species' behavior and adjust their activities accordingly. Some dinosaur species move in predictable patterns based on food availability and breeding cycles. Human groups learn to recognize these patterns and adjust settlement activity. In some cases, dinosaurs pass near human settlements without direct interaction, while in other cases, humans must temporarily leave areas to avoid risk. These patterns influence how long human groups remain in one location before moving to another. Environmental conditions shape both human and dinosaur activity. Rainfall changes plant growth, which affects food availability for all living beings. Dry periods lead to movement toward water sources, increasing the presence of many animals in the same areas. Humans respond by adjusting travel schedules and food storage levels. Seasonal cycles guide planting and harvesting activities, as well as movement between different regions. Human groups develop memory systems that track environmental changes over long periods through observation and record keeping. Communication between distant human groups becomes more organized through established routes and signal systems. Smoke signals, stone arrangements, and patterned markings on natural surfaces are used to indicate movement, safety conditions, and resource availability. These systems allow groups to share information about dinosaur movement patterns across regions. Information exchange helps reduce risk during travel and supports coordination of resource-gathering activities. Craft production expands in settlements where human populations remain stable for long periods. Materials such as clay, stone, plant fibers, and animal remains are shaped into containers, clothing, and tools. Clothing is designed to provide protection from weather conditions and physical environment. Storage containers are made in different sizes for food, water, and materials used in daily activities. Craft specialists develop skills in shaping and combining materials for durability and practical use. Human health practices develop through observation of natural remedies and environmental conditions. Plants are identified for their effects on physical well-being. Clean water sources are prioritized, and food preparation methods are refined to reduce illness. Healing practices involve rest, plant-based treatments, and care from individuals with experience in recovery processes. Health knowledge is shared through direct instruction and repeated application within groups. Predator and prey relationships in an endless prehistoric ecosystem describe the constant interactions between living creatures that hunt and those that are hunted in ancient times, when many different kinds of large and small animals lived on land, in water, and in the air. In this kind of world, life was always active and many animals depended on other animals for food. Every living group had its own role in daily survival. Some animals spent much of their time searching for food, while others spent much of their time avoiding danger. These actions shaped how they lived, how they behaved, and how they survived through time. In prehistoric land environments, many large animals moved across open areas, forests, and wetlands. Some of these animals were plant eaters, and others were meat eaters. The meat eaters depended on catching other animals for food. Their survival depended on their ability to find weak, young, or slow-moving animals. These hunters used different methods such as waiting in hidden places, moving quietly through plants, or following groups of plant-eating animals for long periods. The hunted animals had to remain alert most of the time. They lived in groups or alone depending on their body type, food needs, and natural habits. Plant-eating animals in prehistoric ecosystems fed on leaves, stems, seeds, and other plant parts found in forests, riverbanks, and open plains. They often gathered in areas where plants were abundant. Their feeding habits created movement patterns across land areas. As they moved, they often left trails that could be followed by meat-eating animals. These plant-eating animals needed to stay aware of sounds, movements, and smells in their surroundings. Many of them developed strong senses that helped them detect danger early. Some of them used speed to move away from danger, while others relied on staying in groups for safety. Meat-eating animals in prehistoric ecosystems had bodies adapted for hunting. Some had strong limbs for running, some had sharp teeth for tearing flesh, and others had claws that helped them hold onto prey. These animals needed to eat regularly to maintain their strength. Their hunting patterns often depended on time of day, weather conditions, and the movement of prey animals. Some hunted during daylight, while others hunted during darker hours when movement was harder to detect. They sometimes followed animal groups for long distances before attempting an attack. The relationship between hunting animals and plant-eating animals created constant movement in prehistoric environments. Plant-eaters moved in search of food, and meat-eaters followed these movements. This created repeated interactions in many areas. In forest regions, dense plant growth provided hiding places for hunters. In open areas, visibility made movement more exposed, and both predator and prey had to rely on timing and awareness. In wetland areas, water and mud affected movement, making it harder for some animals to move quickly, which changed how hunts occurred. Water environments also held many predator and prey relationships. Rivers, lakes, and shallow seas contained fish, amphibians, and other aquatic animals. Some of these animals fed on smaller water creatures, while larger water predators fed on medium and small animals. Movement in water depended on swimming ability and water conditions. Some aquatic predators waited near river edges or underwater plants to catch passing animals. Prey animals often moved in groups to reduce individual risk. Water environments required constant alertness due to limited space and continuous movement in all directions. Air environments added another layer to predator and prey interactions. Flying reptiles and early birds moved above land and water surfaces. These flying hunters observed movement below and responded quickly when prey animals were visible. Some prey animals reacted by moving into dense plants or open spaces where escape was possible. Flying predators relied on sight and timing. They could move quickly from above and return to higher positions after attempting capture. Prey animals had to adjust their movement patterns to avoid being seen from above. In prehistoric ecosystems, young animals were often more vulnerable to predators. They lacked full strength and experience, which made them easier targets. Parent animals often stayed close to their young during early stages of growth. Protection involved staying in groups or hiding in areas with cover. Some young animals learned survival behavior by observing adults. Over time, they learned how to react to danger signals such as movement changes, sounds, or vibrations in the ground. Some predators focused on specific types of prey. Certain meat-eating animals preferred smaller animals, while others targeted larger plant-eating animals. This depended on body size, hunting ability, and energy needs. Hunting required effort, so predators had to choose situations where success was more likely. Some predators waited for weakened or injured prey. Others followed groups until an opportunity appeared. These behaviors were repeated across many generations of animals. Prey animals developed different ways of responding to danger. Some became more alert during feeding, while others changed their feeding times to avoid active hunting periods. Some animals fed in open areas only when conditions were calm. Others preferred areas with natural cover such as plants, rocks, or uneven ground. Movement patterns changed based on the presence of predators. Over time, these changes became part of daily survival routines. In many prehistoric environments, groups of plant-eating animals moved together for safety. Group movement allowed more eyes and senses to detect danger. When one animal detected movement or sound, others reacted quickly. This helped reduce the chance of surprise attacks. Group living also influenced feeding locations and resting places. These groups often moved slowly across landscapes, stopping at areas with enough plant food before continuing movement. Predators also adjusted their behavior based on prey group movement. Some predators followed group trails, others positioned themselves in areas where groups were likely to pass. Timing played an important role in hunting activity. Predators often waited for moments when prey animals were separated or distracted. These moments increased the chance of successful capture. Hunting activity required patience and energy control. In prehistoric forest areas, visibility was limited due to thick plant growth. This created conditions where sound and movement detection were important. Prey animals relied on hearing and smell to detect predators. Predators also relied on the same senses to locate prey. Movement through dense plants required careful steps. Sudden noise or movement could reveal location. Both predators and prey had to move carefully through these areas. Open land areas created different conditions. Movement was more visible, and animals could see danger from farther distances. Prey animals in these areas often depended on early detection and fast movement away from danger. Predators in open land relied on speed and direction control during pursuit. These environments required strong energy use and careful timing during hunting attempts. Wetland environments created unstable ground conditions. Animals moving through mud or shallow water had to adjust their steps. Prey animals could become slowed in these conditions, and predators used this opportunity for capture. However, predators also faced movement challenges in wet areas. This made hunting more dependent on timing and positioning. Water plants sometimes provided cover for both predator and prey, changing how interactions occurred. In aquatic systems, smaller animals fed on plants or tiny organisms in water. Medium-sized aquatic predators fed on these smaller animals. Larger aquatic predators fed on medium-sized animals. Movement in water depended on currents, depth, and oxygen levels. Some prey animals stayed near plant areas for cover. Others stayed in deeper zones. Predators used stealth and sudden movement to capture prey. Water conditions influenced visibility and movement speed. Reproductive behavior also influenced predator and prey relationships. When animals gathered for breeding, movement patterns changed. Groups became larger or more concentrated in specific areas. This created more opportunities for predators. Prey animals during breeding periods often increased alertness and protective behavior. Some stayed close together to reduce risk. Others selected hidden or remote areas for reproduction. Seasonal changes in prehistoric ecosystems affected food availability and movement. During periods of abundant plant growth, prey animals spread across larger areas. During periods of reduced plant growth, prey animals gathered in areas where food was still available. Predators followed these movements closely. This created repeated interactions in certain locations. Movement patterns of both groups adjusted to environmental conditions. Some predators had hunting methods that involved sudden movement from hidden positions. They remained still until prey animals came close enough for attack. Other predators relied on following movement patterns over time. Some moved in groups during hunting, while others hunted alone. Group hunting allowed coordination of movement, increasing chances of capturing prey animals in certain situations. Prey animals also used different movement strategies. Some relied on fast movement to escape. Others used sudden changes in direction. Some used hiding places in plants, rocks, or uneven land. Some stayed in water to avoid land predators. These strategies were repeated daily as animals moved through their environment for food, rest, and safety. Interaction between predator and prey influenced population levels of both groups. When predator activity increased, prey animals became more cautious and reduced exposure in open areas. When prey numbers increased, predators had more food availability, which influenced their survival and reproduction. These changes occurred gradually over time through repeated interaction between the groups. Some prehistoric animals developed strong awareness of environmental signals. Changes in wind direction, ground vibration, or movement of plants could indicate presence of other animals. Both predator and prey used these signals to adjust behavior. This awareness reduced sudden encounters and influenced movement timing. In some environments, prey animals used resting periods during safer times of day. They reduced movement during periods when predators were more active. Predators adjusted their activity patterns based on prey behavior. This created shifting daily movement patterns in both groups. Feeding, resting, and moving all depended on awareness of other animal activity. Young predators learned hunting behavior by observing adults. They practiced movement, timing, and response to prey actions. Young prey animals learned survival behavior by observing group movement and reactions to danger. Learning occurred through repeated exposure to environmental situations. Over time, these learned behaviors became part of natural survival processes. Prehistoric ecosystems included many overlapping interactions between different animal groups. Each movement by a predator affected prey behavior, and each movement by prey affected predator behavior. These interactions continued across land, water, and air environments. Movement patterns were always changing based on food needs, safety needs, and environmental conditions. Different habitats created different interaction patterns. Forests created hidden movement conditions. Open areas created visible movement conditions. Wetlands created unstable movement conditions. Water environments created floating movement conditions. Air environments created observation-based movement conditions. Each habitat required different survival responses from both predators and prey. Animal communication also played a role in predator and prey relationships. Some prey animals produced warning signals when danger was near. These signals affected group movement and alertness. Predators sometimes used silent movement to avoid detection. Sound, movement, and vibration all influenced interactions between animals. Some prehistoric predators specialized in certain hunting methods. Some focused on chasing prey over long distances. Others focused on quick attacks from close range. Others used waiting methods near feeding or drinking areas. These methods depended on body structure, energy use, and environmental conditions. Prey animals responded by adjusting feeding locations and movement timing. Over long periods, predator and prey relationships remained active in all prehistoric environments. Movement, feeding, resting, and reproduction all influenced how these animals interacted. Every action taken by one group affected the behavior of the other group. These continuous interactions shaped daily life in prehistoric ecosystems without interruption.